application is reading a mechanical counter that reads the power consumption in household. Well, that needs to be read only like once a month remotely with a little camera. That clearly has a super low throughput, like once a month. But maybe your application is video surveillance on San Jose Airport with 2,000 cameras, everything in real-time recognition. Then obviously you need a beefier hardware. So in terms of flexibility, obviously the nicest thing to do is to run it on a CPU, but you'll only get like sort of one level of performance. If you are using one of the more popular tools like PyTorch that's got mentioned, or you're using TensorFlow, you're getting a fairly decent support for NVIDIA GPUs, and you'll get like a next level of performance and acceleration. And then things kind of get more interesting and more hairy. At the far end of the spectrum, you can actually start thinking of building a dedicated ASICs that will not focus on normal arithmetics that you need for general purpose compute, but will implement all the primitives that you actually need in some specific neural network acceleration problems. You'll focus on doing 8-bit and 16-bit arithmetics. If you are focused only on the inference, you will perhaps add special DSP engines that you're familiar before, but again for different arithmetics, or maybe for convolution, matrix multiplication, etc. And then you'll have some kind of fairly optimized hardware, and that's great, and people build that all the time. And then they also have this ginormous problem of actually developing a software stack that's going to use that hardware efficiently. They need high-level compilers that understand the underlying hardware and that actually can generate compute tasks, use the hardware reasonably efficiently, like with 80% usability, duty cycle, and not like with 8, etc. So that's kind of hard. And then what lies in between, I would say, are implementations that are based on a variety of either FPGA-based devices, which are pretty good, meaning you can do a lot of different things. And we are currently doing that in Western Digital for our sort of product concept device, and I'll mention that in the second part of the talk. Or you can sort of start thinking about some interesting devices like Google TPU that take an intermediary approach and again add some nice compute primitives that can do a few things a little bit better than the GPU. So that's kind of that spectrum of things that people do, and I would say everything here is actually interesting. Okay, let me move on. Okay, how do I?
Quick question: are any of those being used? Are they in process now, or just thought about?
Oh, definitely. I think for some reason, yeah. I'll repeat and answer the question. Let's just try to fix the projector. It doesn't. Yeah. Can I make a suggestion? Can you unplug that USB and plug it back in? That's.
Gosh darn it! It's a risky business.
Yeah, I'm in management now. You can't really trust me with.
Artificial intelligence will take over the world, but we can't run a slide projector.
Well, what I would really want is this. I just want to like. So there was a question from the audience while we were trying to fix some technical problems. Are how much of these things are currently shipping, or how much of these things are actually in production or actually in use? NVIDIA GPUs for sure are in use. CPUs are still, at least for some companies, predominant way how machine learning inference is being done. Google has produced 2 generations of tensor processing units. And for sure, the first one is in active use in their cloud and available, to a variety of cloud customers. And then Movidius, I believe, is Intel. Thank you. Is an Intel device that's also commercially available. So yeah, a few of these are commercially available. DeFi Tech is now a Xilinx unit, and their FPGA solutions are available. Western Digital has a FPGA-based machine learning accelerator in a drive form factor done in a partnership with the French company Mipsology. Oh, there's plenty of things. There's plenty of things you can buy. Also, there's plenty of startups with super cool claims, petaflops, per chip and stuff like that, but that's in work in progress. Okay, so one question that we get often is, so why not using GPUs for AI and ML? Well, they were originally built for graphics workloads by basically implementing a large number of cores that operate in parallel for working on a graphics workloads. And in about 2004, 2005, starting from CERN and spreading all over the world, physicists started using GPUs for compute problems. This is now kind of very, very common thing. It also gave NVIDIA awesome advantage in terms of developing the software stack because they started really, really early on. And I would say for most practical applications today, GPUs dominate machine learning. But when you have a neural network design and you want to actually train all the weights and parameters, this is what people use most commonly. However, there's plenty of space left for optimizations. These are the commercial products, and as any commercial product, they need to satisfy a variety of customers and a variety of use cases, and somebody has to make an educated guess, how they're going to build their silicon. So part of that problem is obviously that everybody will buy into something that they don't really need, and you may be just using compute, and this is still a graphics card, right? So some of the usage could be dark. So that's kind of one thing that's interesting. The second thing that's interesting, okay, and what if you're doing inference? So when we say machine learning, we say that's a neural network where we train the weights so it can do something practical, recognize faces. And that will work just fine in MATLAB. And then when you want to accelerate it, you can try to use a GPU, but you may discover that just for inference, this card is really awesome and can do like a lot of images per second, but the rest of your system cannot consume that. So if you just have a single camera, it's kind of difficult to figure out how to put a large number of cameras to use one GPU card for inference, because now you have a networking problem. You have to get data in and data out. So when it comes for inference, the winning solution is usually something that's smaller, not 200 watts, but maybe watt if it's a camera, maybe 10 watt if it's a server with few of these inference cards. And obviously, NVIDIA has solutions for that, and Xilinx does, and there's plenty of solutions already in the marketplace. From Facebook study published about a year ago, CPUs are currently predominantly used devices for AI and ML. Meaning, when it comes to a practical data center, practical loads, when people set up stuff that works, this is still a predominant hardware usage, which, by the way, is great use for all of us, especially for hardware guys, because it just means that the world is still at the very beginning of building optimal hardware for machine learning computers. And even if you just are a specialist in understanding how to use a NVIDIA GPU card on the TensorFlow, or if you understand how to set up a cluster of 8 Intel nodes with 8 or 16 GPUs, these are hard problems and non-trivial to set up. And if you want to do a machine learning on 8 nodes and 16 cards, you have like a lot of things that you have to kind of figure out to make it work. If you just do out-of-the-box installation, most likely you will not be getting good results. At least that's experience from my team. So this is yet to happen. So there's like, we're at the very beginning, and there's like, hard to say how many years of work, but probably quite a lot of years of work ahead of us to do all sorts of interesting things. Now, when it comes to usage of CPUs, this is an overused chart. You have probably seen it many, many times. We, in the CPU core industry, we have already reached frequency saturation at the beginning of this century. And this sort of, practical limit of something between 4 and 5 gigahertz per core limits the what you can get from the single thread execution. And the general trend is parallelism, and it applies handsomely into machine learning and neural network inferencing problems. And optimal thing is not necessarily to run a large number of high-performance out-of-order cores like IBM's Power 9 or Intel Xeon cores. They have a lot of capability built for software, like what I just said, out-of-order execution. If your problem reduces to matrix multiplication or vector operations, you may be better off with a larger number of smaller cores that run in order and can just really crunch those numbers, sort of like automotive DSPs. So that's sort of the general trend when it comes to compute cores, and I'll cover this with RISC-V architecture in particular. Another thing is in terms of further customization of hardware, is what kind of hardware do you really want to put to do your machine learning operations, or what kind of hardware do you actually need? So there's a neat paper, and it's from Professors Dave Patterson and Krste Asanovic, who happen to be founders of the RISC-V architecture from Berkeley, that actually looked into what are all the basic compute primitives, by looking at all the different algorithms and all the different, starting from simple stuff like search and sort and going into, matrix and vectors and different data structures and tree searches, etc. And they came up with this cool paper where they sort of identified 13 compute primitives. And one interesting thing that can be done then, obviously, is build 13 hardware elements that correspond to these 13 primitives, and then try to work on compilers for machine learning problems that would actually compile for these optimized hardware primitives that give you best performance per watt or best performance per area or whatever is the actual kind of marketing point of view use case. And finally, sort of to conclude this introduction part before I kind of start jumping on the compute cores, what do we really need to consider for future, right? Many people use the term artificial intelligence, which really encompasses a lot of things. So far, like in my world in Western digital, I'm in a world of image recognition. So I'm looking at the accuracies of different neural networks that can do image classification. And then I'm looking what kind of hardware can make that run faster and maybe run instead of at 16 bits at 8 bits and see what really happens with accuracy, etc. But there is more to artificial intelligence than just image recognition. And this actually tells me that we are at the beginning of the beginning, because I've been just talking about image recognition, and what about the natural language processing? What about reading the text and understanding the context and answering the questions? These are all very, very interesting areas yet to be addressed. And the whole field is actually very rapidly evolving. And I would say that evolution in this field is accelerating and seem to have dramatic changes from algorithmic point of view on a 2 to 3 year timescale. On the other hand, if you look at a practical company like mine and ASIC design flow and time to go from like PowerPoint architecture concept to an actual product with a printed circuit board and a chip, the timescale is more like 4 years. So it's kind of risky today. Obviously, many startups are trying because they want to get famous and rich. But But 4 years is a lot of years, and you're taking a risk. Like somebody could ask me in Western Digital, so what should we do? And is 8 bits enough? And I can probably answer, yeah, 8 bits is pretty good today for inference. We can go ahead and do something. But there's likely going to be a breakthrough by going to a smaller number of bits and successfully doing training and inference. There's likely going to be breakthrough related to some of the analog compute methods. There's like a lot of breakthroughs that can happen, and if you commit early, by the time you come out, you're kind of obsolete. So somewhat tricky. Okay. So in general, the conclusion of this part is then we need some kind of programmable approach. So FPGAs are interesting. We also need some sort of scalable approach where RISC-V becomes interesting, and also approach where it's easy to configure things, where you have a freedom of configuring and creating new instructions, which again, where RISC-V is interesting. So I'm going to jump more into details related to RISC-V, and I just have a question for you guys in the audience. How many people have not heard about the RISC-V instruction set? Like who are the people who are new to that? Okay. And did you guys during your education had the chance to like see a computer architecture book by Professor Dave Patterson? Did you have it? All right. Okay. So cool, because this gives, so then you know everything. You just don't know the keywords. So what exactly is? Let me see. Where am I? I'm jumping to the SweRV core. So just a little bit of an introduction on the RISC-V. So RISC-V is an instruction set architecture standard, which really started at Berkeley, probably by the paper by Dave Ditzel and Dave Patterson from I think 1980, where and paper is reduced instruction set computer or RISC, you can have skin the cat both ways, and very often even people who start with RISC end up with something that's kind of complex and has a lot of additional instructions, like RISC-V standard now does. But the general idea of the RISC computer is to have a small number of instructions to target as much as simplify formatting for instruction encoding, to not try to implement too many complicated instructions that can be, from performance point of view, done equivalently, but just by using a few additional instructions and maybe sacrificing instruction bandwidth a little bit, etc. That's roughly how the idea started, and that's an important part of the idea. But it turns out there is a radically more important part, which is the instruction set architecture, is the encoding of the add instruction, right? When you do a addition in C and when something eventually reduces down to in assembler to add to register and place in the third register, is that protected by a patent, licensing agreement, and other sort of legal difficulties? And it turned out in history, yes. So Professor Patterson and Hennessy worked on a first kind of RISC instruction encoding, but this went into a variety of companies that figured out legal ways how to actually protect the encoding itself. So if you start implementing these processing cores by yourself, you end up yourself on the wrong side of the lawsuit. So this is actually how RISC-V actually came about 5 years ago. It was, I think, approximately 30 plus years after first RISC paper and first computer architecture book and first simulators that could do RISC computers. During one summer in 2014, I think Professor Kirst and his grad students came up with a new sort of instruction encoding, use all the latest trick that can think of. And there was a lot of people in the industry that kind of participated in early phases, and they decided to make it a standard. And they protected that standard by a research study that actually looked into the variety of papers and expired patents that covered all the instructions in the base instruction set. And foundation was started. I was very interested in this topic, so my previous company, AGST, kind of jumped on board relatively early, and RISC-V Instruction Set was born. The RISC-V Instruction Set is available, is provided with a BSD license, and anybody can have it. Your company doesn't have to be a member of the RISC-V Foundation to play with it. However, if you have a product, and if you want to call it RISC-V and use the trademark, then you actually have to be a member of the foundation. So that's the essential values of being a member is that you can use the trademark and you get early access to the committees while people are discussing instructions. So in the case of machine learning and neural network inference, the vector instructions work group is a group that's interesting to a lot of smart people from a lot of important places because this is going to be a first open architecture supported by GCC compiler, LLVM compiler that anybody will be allowed to implement. So this is kind of a cool thing. And I would say this is more important whether that this is still truly reduced instruction set, because I don't really know the theoretical boundary when you say, well, come on, this is not reduced anymore. This is quite complex. So that's unclear.
Can I just ask a question?
Absolutely, I really want you guys to ask as many questions.
You mentioned that instruction sets are encoding is protected by patents.
Not for RISC-V.
Yeah, but I thought that typically a company like Intel typically protected their architecture through the way that the operation of the instruction was the way they protected the patents, rather than like copywriting or somehow patenting instructions in format. How the instruction behaves is how they protected the patent. That's not.
There is countless. I do not know exact numbers. I wouldn't be surprised if it. Actually, let me repeat it. They told me to repeat the question.
Okay.
So the question from the audience is how are really instruction set? What are the mechanisms for protection of instruction set, and can you really implement x86 compatible computer by your startup or not? The answer is for x86 or ARM, you cannot. Basically, licenses, for example, for ARM, if you want to build your own ARM, IoT device with a simple in-order core that can run some simple software stack like in Arduino boards. If you want to use ARM instruction set so that your board can work with ARM GCC, you need a license from ARM, and this is a commercial license. So depending on the size of your business, that has to be paid for. Similar is for x86. I mean, you have to talk to Intel. Yes.
So I've made hundreds of thousands of dollars advising companies on exactly that subject, and they keep coming back, so they must like what I say.
Oh, cool.
I also work on Untitled Systems, which is one of those x86 startups, right? The gentleman is actually correct. It's the way that individual instructions are encoded, not the pattern of the opcodes, which can be protected. The pattern of the opcodes actually is one of those things. It's like a phone directory.
Yeah. Sorry, I misspoke. No. The actual encoding of instructions is what's protected.
Right. And so if you want today to make an Intel compatible processor with SSE instruction extensions, you can actually do that because all those patents are gone. They're all expired.
No, I would disagree with that.
SSE, I guarantee you, this is absolutely true. It's the more recent stuff, AVX.
Yeah. Well, then you will not get, then you will not get the benefit. But certainly, if you want to implement a full ARM v8 instruction set,
less than 20 years old.
Exactly. Then you need a license. Yeah. There could be things that are super old, but then they will not work with the latest software. So it's a questionable usability. So this is where RISC-V come in. Number one. Number two, where RISC-V come in are basically the fact that there is a base set and there are extensions. So there's a large number of work groups in RISC-V that are working on extensions, and this gives community an opportunity to participate in adding new instructions that will be supported by compilers. And many talented individuals and interesting companies took and are currently taking advantage of this. And on top of that, since from inception this was envisioned as a kind of future computer standard, there is a part of the instruction encoding space that's reserved for proprietary, instructions. So if your company wants to have some secret sauce, and then there's a part of the code space that they can use specifically for this, they have a guarantee from standard they're not going to get into collision with the future compilers. But then they have to build their own compiler extensions or do assembly inlining or figure out how they're actually going to use those features. Cool. All right. So RISC-V cores and SweRV. So SweRV is a core that was designed in my team, Invest in Digital, and is open sourced and is now available in an organization called CHIPS Alliance. And CHIPS Alliance is envisioned as a open source hardware and open source design and verification tools for chip design org. And eventually, we want to generate a fully open design methodology from RTL simulators through design verification flow to place and route and synthesis. Eventually, in some far future, we want to create partnerships with some foundries, get open PDKs, and sort of create an open flow. Right now, that's the dream. The focus is on the more immediate projects, which are RISC-V cores, some other interesting pieces of IP, like open source neural network inference IPs, open source RTL simulator tools, open source design verification tools, etc. Current members are these listed on the slide. There is a couple of super talented individuals that joined individually. It's Wilson Snyder, who is a creator and maintainer of Verilator RTL simulator, and Olaf Kingren, who is a creator and maintainer of the Fuse SoC package manager for open source cores. Absolutely.
Regarding, you mentioned open source design verification tools.
Uh-huh.
I think one of the things that's, I myself have kind of looked at that's really lacking is design tool portion. Like something you could use after, let's say you graduate from college. Right?
Mm-hmm.
You want to do some personal projects, and it's never like up to the standard
Correct.
of commercial tools.
Correct. So the big idea of a CHIPS Alliance is to pool large companies that are actually interested in creating. This is sort of like 20 years ago with Linux. 25 years ago, nobody ever thought that it would be possible that compilers or operating system kernel would be available in open source, right? So, and compiler part was kind of an important part of the whole story. Getting GNU tools to work allow this to happen. So we got really good design and design verification and software experts for CAD tools, and we'll try to tackle this. Maybe we'll come up with the conclusion it's not really doable, but we're really going to try hard by starting with some specific projects rather than attacking everything. Interesting enough, in academia, there's a couple of academic projects that have a fully open flow. And there's a couple of startups that also generated successfully chips with a fully open flow in 180 nanometers. So it's not like entirely impossible. OK, let's move on. So what is the CHIPS Alliance? I already kind of said all this. It's an organization which develops and hosts high-quality open source hardware code, like IP cores, like SweRV, that I'm going to talk about today. Some interesting interconnect IPs, and open source software development tools for design, verification, simulation, etc. It's meant to operate very similar like RISC-V. So it's kind of started from people from RISC-V. We copied the RISC-V bylaws and participation agreement, and then started modifying it as appropriate for hardware. And we're still, even though we launched, we're still modifying because there's so many things that are different from hardware than for software. But we like it to be like RISC-V. So we are working on, we are forming committees that will discuss roadmaps for IP improvements, and people will contribute engineering workforce trying to generate verified IPs and similar stuff for the tools. And the idea is you share resource, because reality shows, like for RISC-V cores, you don't really need like thousands of RISC-V cores. You kind of need RISC-V core for each of the market segments, and you want to make them in open source to allow opportunity for further optimization for those individuals or companies interested to adopt it. So we want to share some of design verification. That's the idea, so that not everybody has to do everything by themselves. And this makes a lot of sense, especially since a lot of companies spend a lot of effort and then they open source. So we're kind of trying to. There's a question from back of the audience.
Could you elaborate on the interconnect IP? Is it different from actual trace and route? If you wanted to do actual trace and route, you do need some library which
Yeah.
is hardware related. So do you assume something or you don't assume anything?
Okay. Let me repeat the question. I'm not sure if this gets recorded. So the question is for the interconnect IP, what do we have in mind and what kind of projects we are going to have in CHIPS Alliance? Currently, one that has been announced and contributed, and it's on a GitHub for CHIPS Alliance, is OmniExtend. OmniExtend is a standard for encoding tie-link cache coherence and interconnect protocol from Berkeley on top of Ethernet frames. And it allows building an SMP system with using commodity Ethernet cables and commodity barefoot network, now Intel programmable switches. So that's like an example of what we mean by interconnect. There will be few more things coming, but they're still kind of in a private phase. All right, and shown on this chart are year on the x-axis in the increment of 2 years, so 2012, 14, 16, 18, 20, 20. And on the y-axis is sort of not so super accurately defined axis that assumes low power and low performance for low values of y. And then as you go up on the y-axis, it's a higher performance, but also higher power. And these are the subset of the RISC-V cores that I was aware of when I made this chart, and for which I could verify that open source definitely exists somewhere and can be downloaded. The first one ever was Rocket Core from Berkeley, and then ETH Zurich in Switzerland became fairly active in making RISC-V cores, and they made RISC-E, Zero RISC-E, and Ariane. These are all the cores here are in order, single issue cores. And then from Berkeley came also Boom, Berkeley out of order machine, and in two variants, V1 and V2, and still actively being developed in Esperanto. And one thing that you may notice, and I didn't have enough space on the PowerPoint, but there's kind of a big vacuum here in between. There's a level of performance that you get from in order 5-stage classical pipeline, and then something that you can do with super-scalar out-of-order machines. And in Western Digital, when I joined RISC-V, I was mostly interested in the RISC-V data center CPUs, but RISC-V idea really, became popular, and our ASIC design teams for flash controllers became very interested to have an open source, in-house open source RISC-V cores, so they can develop cores and really optimize them for our workloads. And this is interesting things because you can remove a lot of things that you don't need and make a lower power and lower area. And it's a nice thing that you can do inside a company, because when you're getting commercial IP is well-packaged, well-verified IP that an IP company develops for a large set of customers. And they don't like to customize it because, and that's why they charge NREs. They don't like to customize it because when you start customizing, you have to verify it again, have a lot of issues, a lot of problems. So it's not uncommon for you when you license IP that you buy something that you don't need, that you actually have a dark parts of your IP that are there, maybe are taking area, but they're not really being used. So this became quite popular. And there was a need for intermediate performance score. Sometimes I get questions from young folks from Berkeley who are very well versed in RISC-V. Why was this needed? We have a lot of legacy firmware. And legacy firmware is essentially a single program. It's a one program that runs on one core. And modern way to accelerate it will be, well, to rewrite all the firmware, make it run on 4 cores, and get it to run faster. But this requires more firmware development and more validation, verification, qualification of the products. And that's expensive and takes a while. And some of these products are consumer devices. People still expect reliability from their USB devices, but they also assume that they're virtually zero. I don't think anybody would like to pay USB more than a few dollars and prefer to get it for free on a conference. So in that kind of scenario, you reach this point where you have this legacy firmware, and your number of operations per second actually becomes limited by the program execution, and you would just like it to run faster, and you don't want to rewrite the code. And then what's the way to do that? Well, you make something that runs at a better performance. And that's actually how SweRV emerged. And I'll give you the details what we have done. We built what's called a two-way, meaning 2 instructions issued per cycle super-scalar core with 4 ALUs, etc. I'll give the details. Something that's in intermediate performance. Go ahead.
When the note there says 5 cms per megahertz.
I'll explain what, because I'll have an actual performance chart. But
the second question is the 0.1 millimeter area.
Yes.
What process technology?
28 nanometer. It's going to come. Sorry. This was a summary chart for meetings where I don't actually show the detail. Today I'll have like a lot more detail. The question was, what do these 2 things mean? This is a performance number, 5 Coremarks per megahertz. I'll explain in 10 slides. And this is the area, 0.1 millimeter square in 28 nanometer. That was the target. So this core right now is available in Chips Alliance. And what you see as a sort of dash line things are things that we are working on right now. And it will be first available when it's in alpha phase to the members of the Chips Alliance. And hopefully by 2020, it's going to be widely available. This is an upgrade to the current SweRV core, so a little bit even more performance. And then there's going to be a really, really small core. And then in 2021, 22, there's something really, really high performance. So more things are coming. SweRV is a line of core, and this is just the beginning. Go ahead.
So when these cores are released, are they released in some standard language like Verilog?
Yes.
All of them, they are validated with industry standard simulators so that the wide audience can
Yeah.
over them.
So I'll speak about things that came from my team. So SweRV core is written in Verilog and System Verilog. It has been done by a team of seasoned CPU designers with probably combined experience of 300 to 400 years from Sun, from IBM, and from Intel backgrounds. The IP has been developed with design verification methodologies appropriate for CPU cores, which is a very sort of tribal knowledge of how you do the random instruction stressing of the core, exploring all the corners in the design, mixing it with interrupts, mixing it with everything that's kind of known from the history of previous projects to come with robust design. And then it's transferred as a verified IP to our ASIC team that's actually putting it in the product. So it's not an enthusiast core. And we open source the whole design, programmer's manual. And we are working with third parties through Chips Alliance to sort of use some of the open source verification tools that would allow us to give more of our verification test benches and things of that nature for which we use commercial tools, so we can really open source them. So we are trying to figure out that part as well. It's a hard part. You can ask a million questions, no problem.
You started to explain here what the
Uh-huh.
Following his question, that the quality of verification is something that you guarantee, or what kind of quality of verification then your IP code is going to fully execute your ISA in all conditions. For example, when I was
Uh-huh.
working at my previous company at IBM, so we did their 10 billion cycle simulations, but that only runs in like 10 seconds in actual hardware. So actual hardware verification is whether it runs at or whatever speed it is.
Yeah.
It's extremely important.
Yeah.
So that's for the verification.
Let me repeat this part of the question. You can, I worry now that I will not be able to repeat the whole thing. I don't have enough slides on this topic, but maybe I answer immediately because it's a very good question. So gentleman has asked, what kind of guarantees adopters of SweRV core have that it's free of bugs? And number one, I think, question. Number two question is, what kind of methodology was used in the design verification of the core itself? The guarantees are described in the headers of these files, carefully written by experienced lawyers. The cores are obviously available as is under the Apache v2 license. The methodology that has been used is a tribal knowledge of verifying compute cores. And we typically have internally 3 release cycles that we call alpha, beta, and gamma. In each cycle, several billion instructions have been run through our COSIM environment. The instruction set simulator that was used as a golden standard in our COSIM has been open sourced. It's called SweRV ISS, and it's available. Typically what we've done, we done in parallel the RTL simulation with 3 commercial tools and 1 open source tool, Verilator. And we do aggressive testing, through the all space of possible scenarios, including random generation of instructions, interrupts, CSR states, stop and go, etc. And we do the comparisons, between the RTL simulation and the golden model. The CHIPS Alliance is actually looking into this specific problem with the help of Google. I don't have a chart on this, but with the help of Google, there's a cool tool called STIG that's actually available through cloud that uses the Metrics RTL simulator and Impera's golden model instruction set simulator to run a similarly stressful test, trying to go randomly through all the instructions. So that's one thing that we are doing in CHIPS Alliance. I kind of wanted to release all my COSIM environment to open, but there's a problem of the tools, right? So you kind of have to be very careful about these things. You cannot release other people's IP when you're trying to go into open source. So. Go ahead.
On the same subject, you mentioned about the IP is written in the Verilog or something like that.
Verilog and System Verilog, yes. Yeah. That's a standard today.
That's right. So that doesn't surprise me, but it is a very good thing to do. The question is, how much of that Verilog is synthesizable, so-called? Can I just run some standard TSMC or some companies standard cell flow and really synthesize, or how much of that is a synthesizer actually? If someone buys the IP, then
yeah. So let me repeat the question. I'm not sure that I understood 100%, but I can describe you roughly our flow because it's relatively standard. The question is, how much of the core is generated in Verilog and System Verilog, and how much of the core is synthesizable?
That's right.
Yeah. So our core is written in mostly in Verilog and 100% synthesizable. It's targeting ASIC, but when we delivered alpha phase to our ASIC team. And we only tested with Cadence, Synopsys, and Verilator. They actually ported the core into their ASIC environment and did the FPGA synthesis, and they got the core was running immediately. So it's, for example, synthesized for FPGA, no problem. The flow that we have is we mostly design our IP in Verilog. For the design verification, we use system Verilog. And then we use commercial, we have to, except for Verilator, everything else are commercial tools because, we have a product to build. So we can't really play yet with open source flow. But in Chips Alliance, we want to tackle that. Did I answer your question, or I kind of missed? Okay, all right. In addition to that, the core is very parameterizable. So pre-synthesis, you can actually choose a bunch of parameters, when you generate your core. I actually did put this chart. Ding it. Okay. All right. So I just did this today. I forgot. So this is the Google's contribution to Chips Alliance. It's a design verification using a COSIM with reference model. So Google has a randomized instruction stream generator written by engineer with last name Tal. The post GCC compilation, the L files replay to the RTL simulation, which is done through Metrics, another Chips Alliance member, and through Imperas ISS, which is a golden. This is a company that specializes in instruction set golden models. And then obviously these get compared, and an attempt is to really heavily stress the core through every possible corner case that can be thought of, or that happened in the previous projects, or that your ASIC team catches when you deliver the IP, etc. We are in good position in my team because we have a customer internally that's committed to use the core. So in addition to verification that we do with design verification team, that's actually co-located with the ASIC team. ASIC team takes the core, now is building the ASIC, so we get like a lot of early usage through our alpha and beta phases, a lot of feedback, bug reports, etc. So that kind of gives you kind of an additional idea of that SweRV is not an enthusiast core, but something more close to product. And another interesting project that we have in a Chips Alliance that I want to plug in here is the Fuse SoC. Fuse SoC now supports SweRV, and it's a package manager and build tool that allows you to pick different pieces of IP, like RISC-V cores, UART, and build an SoC. And you can choose whether you want to run it in, and it supports a lot of interesting things. So Fuse SoC already supported Zephyr RTOS from Linux Foundation. So when we implemented support for SweRV, we were immediately able to run Zephyr on our core. And that was kind of cool. It was basically a consequence. And what this tool does, the magic that it does in the middle is called Core Manager, which is resolving all the dependencies between the IPs. So when IP is added, it works. So currently you can target Verilator RTL simulator, or you can target through Vivado, you can target Nexus A7 board. So you can play with different, and supports some cores that are not RISC-V. It supports Libre open RISC cores as well. Which is an interesting feature to mention about the Chips Alliance. Chips Alliance is a very friendly place for RISC-V, but it's in general open source organization. So other instruction sets are more than welcome to the Chips Alliance. This is important. I was hoping somebody would ask, but IBM yesterday announced the IBM Power Instruction Set Architecture being open, which means that you can now start thinking about building your own power processors. So that's a cool thing.
Is that based on Power 9?
Yes, it's based on the Power 9, and they'll set up a work group in Open Power Foundation, which is now a project inside Linux Foundation for kind of community, development.
I see the logo there.
Yes, I try to get stickers for projects that I participate in. Verilator is if you are in the ASIC business and you haven't heard of Verilator, check Verilator out. It's a 20-year-long project started by Wilson Snyder, true genius. He has started this out of kind of excitement, and it has grown into a serious tool. And I use it in my team. Many other all the companies I interact with, I discovered they use it. It's really super fast. So if you want to kind of break the record in your RTL simulation speed, this is a way to go. And uses multi-threads really well, etc. All right, so SweRV core. So SweRV core is a RISC-V core that supports 32 IMC instruction set from RISC-V. For those of you who are completely new to RISC-V, 32 means 32-bit core. I means integer arithmetics, and this is a mandatory part. The minimum support that you can have is RV32I. There is no 16-bit architecture in the standard, and obviously you need integers so you can compute something. The rest is optional. So M stands for multiplication and division, meaning that there is a hardware for multiplication and division in the core, and C stands for compressed instructions, which is encoding for a subset of instructions that allows normally 32-bit instructions to be packed into 16 bits. Super popular thing in embedded companies like Invest in Digital. Very important that this works well and that your code can be compressed to the minimum that architecture allows, and obviously gets compared against every possible commercial architecture. We support RISC-V standard debug support, programmable interrupt controller. We support HB Lite and AXI buses. These are kind of the standard buses that are needed in a company like Western Digital. In super ideal world, I would have wanted to have supported tiling from the get-go, but not yet. And the targets that we got initially from our partners in the SSD business were to get 1 gigahertz at the SSG process corner and to target 28 nanometer TSMC technology. So, and I'll have the charts to tell you how we have done in which process corner we exceeded this. The exciting part, so what was exciting here for me, right? I got these awesome people that I have hired that came from IBM, from Intel, from Sun, brought a lot of experience in designing both the compute core in compute companies and high-performance embedded core and embedded cores in different embedded market segments. And what we wanted was a higher performance core, something that beats the classical MIPS pipeline. And I'm careful treading this topic with Professor Patterson and other important folks from Berkeley, because they'll say that all that you will ever need is a classical pipeline. But again, it's true if you have a lot of programmers and if rewriting a software is not the problem. So in academic project, it's kind of true. In practical company that ships, I don't know, 12, we make more than 12 SoCs per year, and nobody really knows how many different SSDs and HDDs we have. Like there's part numbers galore. So you don't want to keep writing firmware like for all of these things. So legacy is a reality. So we wanted something that runs faster. So what are the things that you can do in the core to make it run faster? There are several things. You may want to stay in order to keep the core small, because the size of the ASIC for the SD card, SD card is this big, so you're not going to have a centimeter square ASIC. It's not going to fit. So you stay in order. What you can do is add more stages in the pipeline. When you break the compute process from fetching, decoding, doing useful things, and committing back to memory or to register file, you can do this in one step, like one cycle core, or 5, like in classical pipeline, which makes sense, or go more. And when you have when you have a larger number of steps that take smaller amount of time, the consequence is that you can run at a higher frequency. So that's a nice thing. You get some acceleration from that. Then the second thing that you can do, you can build a super-scalar core. Super-scalar core means you'll start fetching multiple instructions per cycle, and you'll have 2 execution pipelines in which you're going to actually execute these instructions. So this is what we have done. We actually have 2 execution pipes. If you have 2 execution pipes, and if you have a perfectly random generated code that doesn't really, the instructions are not correlated to each other anyway, don't hitting the same registers, etc., you can kind of get a double acceleration. But that's not really realistic. Realistically, when you have a code, the same registers will be referenced, and what you can realistically accomplish with a dual pipeline and a 2-way issue core is about 25% acceleration. Then the next thing that you can do, that you may notice if you look at our execution pipes, we have these 9 stages in the pipeline: fetching stage, aligning stage, when we form instructions from the actual buffers, decoding stage, and then we are committing up to 2 instructions per cycle, and we have a separate load store pipe that will interact with the memory. And we have a multiplication pipe that will handle multiplication in the pipe. And we have a divider that's outside of the pipe. So we trap sort of a division instruction, and then we start the division hardware and get it done in between 15 to 34 cycles. So the main action happens here in these two pipes. We can do arithmetic operations at 2 places per each pipe. And a lot of people who only had an education in a classical pipeline, like I did from Professor Patterson and other computer architecture books, look at all this stuff, wow, 2 pipelines, 4 execution units, what's going on? So what's going on is kind of cool, and we'll have a pipeline diagram to kind of walk through that. But you can get instructions like add that wants to add 2 registers and place in the 3rd register. And if it's really just with registers, you can do it here. And if it's unrelated, you can do it here as well, get a lot of parallelism. But it doesn't really always happens like that. More commonly, you have something that's called load to use in most computer architecture books, meaning you're loading from memory into a register, and then you're doing something useful. Now you're adding 16 to something that you loaded from the memory. And if that's the case, that load takes some finite time, and you miss this opportunity. And in a classical pipeline, you'll have to stall until you get the data, and then you continue. Well, in this design, you actually continue, you don't stall the pipeline. And as long as your load actually is done in 2 clock cycles, you'll be ready, you'll get your second chance. And then this is how you actually design your hardware, this is how you design your caches. So that actually works kind of nice for embedded systems. We have a tightly coupled memories for instruction and data caches. We try to fit our code into instruction cache that we have. And obviously, not everything can fit into our data cache. Sometimes we have a miss and we have to go to the slower flash memory, but that's okay. But your normal latency of 2 clock cycles is nicely handled by the second set of execution units. And this, it turns out, from the experiences from companies like Freescale and Intel, this gives you kind of additional 20 to 25% boost. So overall, this kind of design, when renormalized to frequency, can beat the classical pipeline by about 45 to 50%. And I'll show you the Coremark data that actually proves that. On top of that, it actually can synthesize and run at a higher frequency because it has a deeper pipeline. So it has some frequency advantage. Go ahead.
2 questions. 1 comment and 1 question. So my comment about this microarchitecture is kind of it's eerily similar to, and if I mention this, then I guess.
No, that's completely okay. There's no questions are off limit.
People know how many years I've been looking at this stuff. It looks like Cyrix is in one microarchitecture, if you know what that chip is. It's called 6x86. It looks very similar.
Yes, yes. So you can go. I checked this on Wikipedia to kind of try to figure. It's difficult because different people and different experts, they kind of grew up separately in different companies, so they call the same thing with different names. So it's hard to like trace all this. By talking to the people with much more, you don't have any gray hairs. By talking to people much older than you, I sort of figured out that this happened first time in Freescale. Now, this is a risky thing to claim. It's entirely possible there's another company before Freescale in the 1995 that done it, but it seems like it happened in Freescale.
To me, it looks a little bit like Cyrix's
Yeah,
A1,
yeah.
To me.
Yeah, and I think that came after Freescale chip, and then
that came out in '94. They announced it.
uh-huh.
So it might be a little bit before Freescale.
Yeah.
But I'm sure he knows.
Yeah.
The second question
And then Intel has one of, Intel had a similar design at 1.2, I think, for 486.
The second question about the microarchitecture is
Uh-huh.
why do you need an aligned stage, pipeline stage? It's a RISC processor. It's already the instruction.
Because of the compressed instructions. Yeah, because compiler will generate compressed instructions, and you'll have to handle this binary where sometimes you have 32 bits, sometimes you have 16. So you need to make sense out of it.
So if I were to follow up that question, so if it didn't have the compressed instruction, you don't need that line stage. It's pure 32.
Correct. Yeah. So let me. I'm keep breaking the rules of YouTube recording. So the first question was when was this design, microarchitecture design, used for the first time? Audience suggests Cyrix. I thought it was Freescale. It's entirely possible that both are true. Historically, when Mike Johnson, there's a book, Super-Scalar. Yeah. I think he was one of the kind of original inventors, at least in patents. So we will have to ask him. The second question is, why do you need an aligner? And aligner is needed because the compiler tool will generate, and we'll see later how good, will generate compressed instructions. So you'll have this flow where some instructions are encoded as 32 bits in memory and some are 16. So you need to have an entity in the pipeline that's actually going to discover beginning and end of instructions and then unpack and understand the compressed instructions. Did I see a raised hand? Go ahead.
It's unfair that I should introduce myself. My name is Sangong. I asked you too many questions.
No, Sangong, that's totally cool. That's okay.
So unfair if I don't say my name. So there are a couple of questions. Your multiply pipeline is a 3-cycle latency. So that means that you are only doing, at least in this code, only integer multiplication.
Yes. This core doesn't have a floating point, nor we need it for the storage controller firmware, code.
And the second question is load store pipe. Load to use penalties as 2 cycles, which makes a lot of sense. Then you didn't say anything about the cache itself is a one read port or one write port. So what happens if you have a load and the store instructions? You dispatch 2 instructions, right? So
Yes.
so do you store, or does your pipeline stores, or
It does.
it does?
It does. It has to.
And then when you do the commit, do you do it in order, programming order, or you?
That's a great question. Thanks for asking that. All right, so let me repeat your. That's my favorite question. But the first question was your multiplication pipeline gets the job done in 3-cycle latency. Does this mean you're only supporting integers? Yes, and it says that on the previous page, 32i. If we supported floating point, there would be f. The second question was, does your core does stores? Yes. Answer is yes. And the third question was, is your core perfectly in order, or maybe you're cheating sometimes? So that's another sort of tribal experience from the industry, which is when you do get a load that actually missed and needs to go to the slower flash on the platform, this is a larger number of cycles, potentially, I'm not supposed to say, but say much larger than 2. If it happens, no, this is normal. Guys, this is normal. You put some flash and you don't want to spend a ton of money because this doesn't happen all often, so you optimize it for size and not for the latency. When that happens, if the subsequent flow of instructions after the missed load is not referring the registers that participate in the load, Core will actually continue executing and doing the scoring in hardware in real time to see when that register, only when that register gets referenced, then it will stall. So we allow that little bit of out of order execution. So it helps in those corner cases. It helps a lot. It allows firmware programmers also to be aware of it and write the code in different ways, etc.
Thank you.
My pleasure. Go ahead. And please remind me to repeat the question. I keep forgetting that. The question is, you have 9 stages pipeline with potentially 4 stall points. We call it only 4 stall points. They're as listed as here on the fetch, on the line, on decode, and commit. Yes, those are your potential stall points. You really measure the performance in 2 ways, almost even 3 ways. The first way you measure the performance, you run the benchmark, like Coremark. The second, oh. So a question from the audience is, because of the interrupts, your reality is, the second way how we evaluate performance is we run the production code. We generated these benchmarks, which we also open sourced. So these are the benchmarks typical for flash controllers. And we actually run real firmware to compare our core to commercial cores. So we have been actually very successful with performance. And I agree with you. We do run in an environment where there's plenty of interrupts. That is actually correct. But that's what it is. Performance is what you measure, right? I mean, it's.
This is a comment to that question. Usually, when you say an interrupt, it's external interrupt, and the external interrupt can never be a synchronous event. There is no way you can make it asynchronous. So because of that, I think as long as you're talking about external interrupt, the 9 pipeline stages and that is pretty much independent as far as I know. Yeah.
Correct, yeah. Yeah, I agree with that.
So there are other type of interrupt, which is like trap or exceptions, which is your instruction itself generates exceptions, like a load, you just have a miss. In that case, it's different.
Yeah.
Yeah. So you have to one should make a difference between external interrupt versus the program, instruction is generated.
Correct. Correct.
I'm just agreeing with you.
No. Those are all fair comments. Again, you do have your real environment, which is a completely practical device that unpacks the host controller interface commands and trying to do useful thing by writing or reading to media, operating the ECC engine. So you can compare that against different architectures and different cores, commercial, open source, etc. We only define performance relatively. We don't necessarily define performance toward some absolute ideal thing when the pipeline is flowing without any stalls. I actually never even looked into that. I don't know if that was the question. I wouldn't even know how that compares. Basically, in other words, we only have to be better than commercial IP core. We don't have to be ideal.
I think one way to look at it is processors, depending on how they're being used, they're going to, say, a PC, then you want fastest single stream performance. But if this is a small core that's being used for
Embedded controller. Yeah.
programmed by firmware to control hardware,
Correct.
then the interrupt latency is a very significant attribute of the processor.
Oh, absolutely.
Why, for instance, it may make sense to go to super-scalar for a central processor in a large system, but not necessarily. So, for instance, I believe even today the 8051 is still the dominant processor for firmware, embedded firmware. And one of the reasons is it's very simple, and because it's very simple, its interrupt latency is also deterministic and well understood. So
Yeah.
this is a very real issue.
No. I fully agree. We are. I mean, these applications are interrupt driven for sure. But again, it's the case with other. Competitive cores are not particularly different than things that I'm talking about here, right? So we only have to be better than that. I'll give you a little bit of a spoiler. The next generation core that improves on top of it actually improves the interrupt latency. So we actually did a different implementation and improved the interrupt latency quite a lot. But this one was good enough. Don't get me wrong. This is actually used in and I'll show you the block diagram of the product where it's used.
I was wondering how many slides we have left to cover.
37 is total, so I'm halfway. Yeah. All right.
So I think we'll probably have to defer the questions towards the end because we have only like 30 more minutes because we spend the event ends at 9 o'clock.
Yeah. Correct. If I just speak naturally, it's about for this presentation about minute and 5 seconds per slide. So it's not I can make it, but I also like the questions. I don't mind.
The performance of the CPU, why use compression with memory cheap?
Oh, excellent question. So now you learn something about flash controllers and SSDs when I answer this question. So the question is, why use compressed instructions? The reason for using compressed instructions is that building microcontrollers for flash, for small devices like micro SD cards and SD cards, embedded flash chips, there is a tremendous pressure on cost and area. And if you can actually design a controller that uses a 8 kilobyte, instead of 16 kilobyte instruction cache, you'll be a champion in a company. And this actually will be used. This is actually most important pressure that I had on this project was inefficiency of the compressed instruction set implementation in GCC. Compressed instructions are well architected in the architecture, but GCC has to actually do it. So a lot of effort I actually put, including hiring contractors and experts with hundreds of years in compilers to actually work that compressed instructions are smartly used. Very important thing for embedded. Every other person I met, like from NXP or from IoT companies, everybody cares about this greatly. Pipeline diagram. This pipeline diagram explains how the dual execution unit stuff works together with the code sample. So instructions are labeled with either L or A. L indicates loads, A indicates arithmetic instructions. The index with the label is just instruction 1, 2, 3 to 7. And let's focus on load 1. You'll notice when load 1 is loading register X11, and after the load 1 comes load 2 and load 3, and instruction A4 would actually like to use instruction A4 would like to use registers X13, which is referenced in L2. Okay, so let's just focus on these two, L2 and A4. So when L2 gets into pipeline, it's going to need two clock cycles in order for register X13 to be available. So when you want to do your A4 operation in the pipeline, you don't have this value ready, and you cannot do it. And in a classical pipeline, you will stall. In this design, you actually continue without stalling, and you were not able to do A4 here, but you're actually able to do A4 with your second chance, because when you get to that second execution unit, by that time, X13 register actually has been loaded. And this is the kind of niceness of this dual executions with some kind of spacing that corresponds to the actual load to use. In terms of the branch prediction, we implemented the branch prediction algorithm called G-share. G-share is one of the branch prediction algorithms described in the Patterson book. And in order to understanding, you kind of have to read all the previous one until you kind of graduate to G-share. And this is about the most complicated branch prediction that makes sense in embedded applications. When you go to your next kind of a thing, it's becoming too much of a hardware, too big, and obviously you could take advantage. You can always take advantage of the better branch prediction, but you want to keep the size of the registers and SRAM that you need to some reasonable value. This has been done really well, and we kind of discovered that we are beating in our branch prediction some commercial products that claim the same algorithm and configure with same sizes. Yes.
Target buffer. Instead of branch target instruction buffer, or it's the address buffer?
Address buffer. Yeah. No problem. I'm getting really scared every time you ask the question, because I think at one point you're going to get me, and I'll say, I don't know. Yeah, I know. Question that often comes, right, is what really happens with branch prediction latencies, right? So if you mispredict in our primary, actually, before that, branches that hit the BTB, that hit the buffer, will have 1 cycle branch penalty. If you mispredict in that first ALU, you'll have 4 cycles penalty. If you mispredict in the second one, you're going to have a 7 cycle penalty. So that's another performance compromise. In this architecture, you'll have potentially up to 7 cycle branch penalty, and you have to kind of just be careful about that. By the way, very common problem for at least if you read a computer architecture book like Patterson, you'll find paragraphs explaining how very complex out-of-order cores that have large number of stages, when they have the mispredict, you have like potentially up to 30 cycle latency problems. But it's a cost of doing business. Instruction set simulator, I'll skip this in interest of speed. It's available on Western Digital GitHub. It's implemented by people with hundreds of years of experience in building golden models for ISS. And it supports a little bit more than what we need. In addition to support of IMNC, it supports 64I, and we are preparing to add a B extension as well, which is the bit manipulation instructions.
Which language is it written with?
C, C++.
No system C?
No. Not too much. Yeah, no. But you can totally check it on the GitHub just to see all the details. Okay, and from bragging rights, it's very speedy. It gives us about 110 million instructions per second, and it's used in our COSIM environment. So you asked the earlier question, what are the targets and details? The SoC that we are building targets 28 nanometers. Not because we don't know how to do 16. It's cost optimization. You make it a cheaper technology, and you create enormous pressure to make a smaller area, right? And then you really, so the cost is a king. In terms of the area, in the SSG corner, we were able to get 1 gigahertz with 0.13 millimeter squares and 500 megahertz operation with 0.093 millimeter square. In the marketing corner, we were able to get about 0.09 millimeter square, less than 0.1 millimeter square, up to 1 gigahertz. That's actually pretty good. It has beaten our target for our SoC development team was to improve on commercial cores by a factor of 20%. We went way more than that. It's more like 2x or 2.5x smaller. Go ahead.
Looking at the microarchitecture in the area, to me it looks like the competitor or the product you're referring to, the commercial offering is ARM Cortex-A7.
Yeah, it can't. Okay, so is that what you're asking? Is that a question?
Is that the one you're...
The audience member is asking, looking at the microarchitecture area, he's trying to guess the commercial comparable core. I would totally tell you if you were not recording for YouTube, but if I do that, I can get in trouble because I get recorded. But I can tell you it's not ARM. This is the measure performance. So there is a benchmark called Coremark that's very popular in embedded industry. The way that performance is measured, it's single thread. So if you have a Xeon, it doesn't help you much. It's a single thread and gets renormalized by frequency. So it takes away the effects of the capability to run at a higher frequency and takes away multi-core systems. So fancy out-of-order cores can attack a range of from 5 to 7. And embedded in-order cores can get to 5, and we got to 5. We got to 4.9. Actually, we get to 4.98, 97, 98 range. That really should be compared with the classical pipelines that typically will give you about 2.5 to 3 range. So we got that theoretical performance that we expected of about 50%. On Dhrystone, we got 2.9 Dhrystone MIPS per megahertz. There is a new benchmark that we are working on. There is a committee on embedded benchmark in the FOSSI, free and open source silicon in Europe. And we are trying to generate sort of a new generation of embedded benchmarks that would be a little bit better than Dhrystone with more granularity. And in that committee, we got people from Sci-Fi, from ARM, from Western Digital, from Embecasm, from several and we are trying to come up with a library of benchmarks so that industry can kind of get just more benchmarks. This is an interesting RISC-V topic, code density and optimization. So it turns out that there are issues with the current implementation of GCC, and we attacked it. There is more details, but it's not yet approved for publishing. We'll have a detailed paper on this on RISC-V Summit in the winter. I think it's going to be end of November. We'll have like a 30-minute paper by the firmware tool manager in my department, where we'll describe all our experiences, specific problems we ran into in the solutions that we have done. The things that you can attack is different optimization parameters for GCC, and then the implementation of GCC itself. And compression is not fully kind of implemented with the same level of granularity that's done in some commercial compilers that are used with commercial IP. So there are improvements that we are doing on a compiler level. And then there are obviously improvements that we have done in terms of exploring the parameter space for GCC. And this is kind of a quick summary. This actually uses our example firmware code, that production code that's supposed to run on this core. And doing different optimizations like OS, which is optimized for size, we are at the 64 kilobyte. At options that use do not unroll loops, we get about 60 kilobytes. If we actually add an LTO, which is a link time optimization, we go to about 51 kilobytes. And at that point, we reach something that looks like a parity with commercial implementations. We had the issues with actually using LTO for production firmware that we have solved in the meantime. They were debugging related, so we can actually use LTO for those of you who are familiar. And then obviously, useful option is MSA restore. It's related basically how the prologue and epilogue code are actually being encoded. And you definitively, there's more than one way how you can do that. You can inline for kind of high performance, or you can have a library functions that will do the prologue and epilogue code. And you can even look into the register usage and shorten your, if you only are using 4 registers, you do not have in prologue epilogue to refer to all the registers in the architecture, etc. So there are ways in optimizations that can be done. It's tricky fighting some of the commercial cores, because RISC-V has an axiom written in the base specification which cannot be changed. Base spec came from Berkeley and was donated to the foundation. There's like a 1 page in the spec, read it, it's very interesting, which explains why there shall not be an instruction that can actually handle your prologue and epilogue code like a multi-load and multi-save instructions that can save or load 32 register with 1 instruction. And an explanation is from the perspective of there's no point of doing that, because if you do it with a function, you'll get the same speed, which may or may not be true. There are tricks of how to take advantage of that instruction. So that's a little bit of an uphill battle, but okay. And this is our actual embedded application. This is a block diagram of multipurpose SoC for consumer SSD applications. And the general architecture looks like this block diagram. There is a host controller attachment interface that will take the NVM Express commands on the PCI Express bus or SATA commands on a SATA 6G bus. And main CPU will actually go through these instructions and will read NVMe instructions, will understand is it read, is it write, what logical block address, etc. Will get the data if it's a write, etc. And then there is a second CPU, datapad CPU, which is our first target, that actually coordinates the NAND channel IPs. These are little IPs that talk the 8-wire protocol on the NAND chips and do the actual reads and actual writes from the media, and push that data during the writes to the encoding and during the reads to the decoding to the error correction engine. Obviously important part so that your USB stick or SD card never really corrupt the data. So that's our very high level, 100,000 feet question.
So for the main CPU and datapad CPU, do you use the identical cores, or do you have a little bit difference between the two?
There's a little bit of difference between the two.
So they're implemented differently?
Yes.
Is it the same microarchitecture? But just implementation is a little bit optimized for the usage.
Yes. Yes.
Question.
Go ahead.
What are the thermal properties compared to existing cores?
So that's a very good question. Roughly in the first order, the power dissipation depends on the area. So we got a significantly improved power dissipation.
Heat sinks, no heat sinks?
This actually is a product dependent. For example, SD cards, you can put a micro SD or SD cards, no heatsink, right? The USB, same thing. SATA SSDs tend to have a bigger body, so you can take advantage of the packaging in some cases for heat sinking, but It's frowned upon because you want to use plastic, not metal. And that's the range. This is like a consumer low-end application we are talking about. We are not using this in high-performance M.2 SSDs, or we're not using this in the 3 gigabyte per second devices, which I believe require heat sinks, which is not normal. So RISC-V and machine learning. How is this related? So we've seen this core already. So you guys know this already. This chart is high level, mostly marketing chart that explains the main trends in the computer architecture. The main trends in the computer architecture is that there is a need for new hardware that is dedicated to the machine learning and to neural network inferencing workloads. And the general purpose CPU has a reduced role now. Its important role, is to run the operating system, run the device drivers for the I/O, for storage and networking, and provide interfaces needed for memory technologies and accelerator technologies. These are kind of the key trends. And the CPU industry is understanding those trends, and it's kind of shifting in these directions. First, there is an attempt to support new interfaces like OpenCAPI, CCIX. Intel is now advertising their own called CXL. These are smarter accelerator interfaces. There are also trends to kind of start thinking, how can you build CPUs for multiple chiplets and potentially support a new interface by the add-on chip technology that can interface with some kind of low latency, high bandwidth physical interface. So these are the important trends. So I would say the take home for this chart is there's a kind of new class of device. It's just dedicated to machine learning and neural network inferencing, and it needs its own interface to the CPU. And in some cases wants to be smart, like wants to access memory coherently, but that's the device that's doing the compute. So important thing for machine learning workloads is how do you support some important hardware primitives that are needed in these workloads. And one important one is addressed with vector instructions. So vector instructions is something that is very special. And I forgot the name, but you mentioned, for example, that some of the later SIMD instructions from Intel that are still protected by patents, you cannot build those solutions. The nice thing about RISC-V vector instructions, they're developed by the community. They can evolve from version 1 and version 2, and they're free. And they have been designed by, I would say, the primary drivers were Professor Krsta Asanovic. That's his baby. If you're interested in a vector processors and vector machines, read his PhD thesis, I think from the late 1990s. He also built many first and second kind of academic vector machines that have been used for many years. And there's an awesome YouTube video by Professor Asanovic from about 6 months ago, from some sci-fi hosted event on the history of vector machines and artificial intelligence. Hardware history, who built what, and not just RISC-V. There's just basically most of the talk is not RISC-V related. It's more like a history of vector computers. RISC-V vector instruction implementation, currently it's the version 0.7.2. One of the goals of the instructions was to do as much of abstraction as possible. It's difficult really to do this in any kind of provable way, but there is an attempt to do the abstraction so that the same code can run on RISC-V vector machines that actually have a different underlying physical implementation. And it's definitely possible to generate assembler code that follows these rules. That's a very cool feature of RISC-V that does not exist in SIMD. So you can have a same assembler code that can run on a machine that has an 8-lane implementation and that can kind of operate on a very wide 8 or 16 wide vector register with a single clock cycle. Or you can have like a small tooling implementation that kind of operates on the same data but needs like 4 clock cycles to crunch all those numbers. It's possible to express the assembler code at least that would be identical and that can run on machines of different strength. And that's a unique and very interesting property. It's not guaranteed. It's going to require a lot of work in community with LLVM and GCC folks, and I'm guessing some startups can do a key pieces of code in assembler. But that's one thing that's actually very, at least to me, it's very, very cool. The spec is at version 0.72, so definitely check that out. It's not very long. It's only like 35 actual pages. It's reasonably readable. This is a part that I copied from Professor Patterson's book. If you're new to vector instructions, this is just a simple example that kind of explains what the heck is the value of this thing. Why do I need vector instructions? If you have to do a DAXP operation, which is vector x multiplied by scalar I and adding vector y, if you don't have vector instructions, your conventional RISC-V code will require a loop, and you'll have to go through this loop, and you'll have to go through array x and multiply each element of this array with a scalar and add it up, and then add y. And you will have to go through this loop as many times as you have the width in your array. If you have a RISC-V vector code, and assuming some neat implementation underneath, your code length becomes significantly shorter because there's no looping anymore. So that depending from the actual width of the registers, you can have like a order of magnitude reduction in the size of the code. And because of improved instruction bandwidth, you're going to get much higher performance. Not to mention that single cycle DSPs for vector addition or multiplication are for at least for integers are quite doable. So you'll get your performance boost that you expect from your hardware. And on top of all of that, you can write your assembler so that the same code can work on some super duper machine in data center and on a dingy tiny IoT camera that needs to spend 500 milliwatts. So that's another kind of add-on. Oh, sorry. Yeah, I have to be in the light. I forgot. I'm drawn by audience. All right, so a little bit of plug-in. I'm excited about neural network accelerators. So I kind of worked on this in my team and wider Western Digital. We have a Western Digital machine learning accelerator. That's how we called it. That's how it's Googleable. It's built in the dry form factor. That's not accidental. It's a U.2 form factor. It corresponds to the SSD devices for the data center that go into PCI Express slots that sit at the front on the server, hot pluggable. So this is roughly how we are positioning it. You can build your storage appliances, and you can give them some sort of in-storage compute capability. You can do some of the inferencing very close where data is. You can take advantage of PCI Express peer-to-peer data movement. And potentially, if it makes sense from use cases point of view, you can even integrate SSDs with some of the neural network inferencing hardware. This card was done in a cooperation with the French company Mipsology, and this is what it can do on benchmarks. I think most of the startups that I meet tend to use ResNet 50 and YOLO V2. So those are the two numbers that worth kind of remembering. When somebody tells you what they have, you can ask, and how much do you get on ResNet 50? So we get 240 frames per second. I think typically NVIDIA cards would be several thousands on the commercial ones. Is that about right? Not 10,000, more like several thousand. All right. But this is also a lower power. This is meant to be a device that fits into small form factor, spends less power, and etc. And matches performance reasonably with the data movement bandwidth, etc. What can you do with small RISC-V cores? This is just my last slide, kind of food for thought. In principle, these small cores, that we built can be fairly small, and I can envision 256 small RISC-V cores with vector unit that can fit into a few millimeters squared. So this can go into some bigger ASIC that has a bigger fish to fry. And it's interesting thing to look like what it can do from perspective of pure number crunching. If you assume something like VLAN, and this is width of the vector registers of 256 bits, and if you assume this RISC-V parameter SEW of 000, which translates into 8 bits width, you can have about 16 times 8 bits wide registers. And if you focus on 8 bits operations, and if you assume that you can get to 1 gigahertz, this kind of subsystem can give you about 8 teraflops, which is a pretty decent number. It's 8 teraflops, few square millimeters, and it can be very interesting for inferencing. That's a very kind of nice room. So this is what hardware can do. I learned this trick from startups that come to Western Digital and pitch for money. They don't really try to design anything. They just multiply the numbers. So I was actually curious when they pitched some of these numbers to me. Can you really get 10 teraflops from? Yeah. So of course, this misses 10 millions of lines of code, to get from practical neural network to the hardware. But that's a easy thing. Go ahead.
Question. This is 1 gigahertz operation, but can it go further, higher than that?
Probably, but I was just throwing orders of magnitude. If I say 1 gigahertz and 60 nanometer for a simple in-order core, I don't think I'll be thrown out of the room. So to conclude, RISC-V is an open instruction set architecture enabling large number of use cases from IoT devices to complex embedded devices like our flash controllers, to compute accelerators, and finally data center CPUs. I met under NDA many startups that are working on neural network accelerators and they're using RISC-V instruction set. The reason is that it gives them a lot of working software. Depending on what they're trying to do, it gives them Linux port, it gives them GCC, it gives them LLVM support. LLVM is very popular as a kind of a baseline to build these high-level hardware compilers. So RISC-V is kind of really, I think we're yet to hear more about it. And there is at least 2 startups that I know of that are targeting full-fledged data center grade RISC-V CPUs, something that's trying to be a me too to Intel, AMD, Power, etc. SweRV Core from Western Digital is a purely practical thing, trying to target embedded controllers that want higher performance for legacy code. That was what was it designed for, and that's what it was being used. This is in a tape out right now. I expect our CTO to hold this prototype device on some of the RISC-V events, probably in the first half of next year. And SweRV Core achieves 5 core marks per megahertz, nice result, and about 0.1 millimeter square area. And large number of open source RISC-V cores are enabling large number of applications, and you have full freedom to add your own instructions, to use standardized instructions, to participate in standards with your point of view and VIN, so that the compiler guys support what you really want architecturally. Now is the time. Now is the time. So that's my last slide. Sorry, yeah. Go ahead.
Could you talk about IDs and JTAG style debugging for Cortex M4 level cores that would be coming out, which would be mainly used in the smart sensing? Because right now in the ARM ecosystem, there's a large fragmentation between multiple vendors and SD-Link versus an OpenOCD, PyOCD. And to me, hardware is great, but software, it makes it happen. And if there is no good support for that in the RISC system, then that's a problem.
I agree, it's very important. That's why we have a debug committee and a trace committee in RISC-V to standardize our implementations. That's what we have followed with SweRV Core for Western Digital, and we work well with OpenOCD. So our FPGA implementations that we put on GitHub are working well with OpenOCD. Okay. In terms of the vendors that we have been working with on debug, it's one of the trusted RISC-V partners, Ashlink. So. Uh-huh.
Doesn't one load interfere with the second load until it is completed?
I think, of course, if they're referencing the same registers, but they're not. I just stole example from the book. It's not very original. But I can.
So I think we have
Yeah.
So many questions during the talk. I think it's at like 9 o'clock is the end time, so it's already 9:05, so let's wrap this up. Again,
Okay.
thank you, Zvonimir.
Thank you, Kieran.
Thanks for
Yeah.
sharing.